Good morning, students. I welcome you all for another session. So today we are going to solve one more problem. Okay, that is analysis of TB. So the problem is like this: a TB of flange width 1200 mm, flange thickness 100 mm, rib width or web width 275 mm, has an effective depth of 500 mm. And this beam is reinforced with 6 bars of 25 mm diameter. Now for this we have to find out what is the ultimate moment of resistance, that is factor moment Mu. So using M20 grade concrete and Fe415 grade steel. Okay. So as usual, first we are going to draw the sketch. Okay. Using these data we are going to draw the TB. Now as you know, this is the flange. Okay, and this will be the web or rib. Okay, now breadth of flange is BF and it is given as 1200 mm. Okay, then depth of flange it is 100 mm. Then width of web, that is BW, is 275 mm. Then effective depth, that is small d, from top of the flange to the center of reinforcement, that is effective depth. This is given as 500 mm. Then FCK 20 Newton per mm square and FY, that is 415 Newton per mm square. Now steel given is, that is the number of bars given is 6 bars of 25 mm diameter. So as a tensile reinforcement there will be 6 bars of each diameter 25 mm. So therefore you can calculate the area of steel. So area of steel is equal to 6 bars into pi by 4, 25, that is diameter square. So area comes out 2946 mm square. So this is the first step. We have to draw the T-beam as per the given data. Now the important thing is next there will be 3 conditions. Okay. So you have to assume either neutral axis inside the flange, then or neutral axis outside the flange. So here one thing I wanted to tell you all, remember how to assume neutral axis, whether it is inside the flange or outside the flange. Now in this problem you have to observe what is the thickness of this flange. Okay, thickness of flange is given as, that is DF is given as 100 mm. Okay, this is less, so very thin flange thickness will be very less, that is 100 mm. And see the area of steel. So area of steel is almost it is 3000 mm square. Okay, so area of steel is more. Okay, then this thickness is less. So automatically the neutral axis will be outside the flange. So in the beginning you have to see what is the flange thickness and what will be the area of steel. So if the flange thickness is less and area of steel is more, automatically the neutral axis will going to lie outside the flange. Okay, or as usual, first let us try neutral axis inside the flange, find out the XU, then if it is satisfied, continue. Otherwise, second case you have to consider, that is neutral axis outside the flange. Now directly what we are going to do here is, in this problem, let us consider neutral axis outside the flange. That is, this is XU now. XU is greater than DF. Okay. So see here now. So let us assume neutral axis outside the flange. So XU is more than DF. Okay. So for this second condition, again there will be 2 options. Okay. One is either DF less than 3 by 7 XU or DF greater than 3 by 7 XU. So let us assume. Okay. We don't know whether this condition is satisfied or not, but let us assume these 2 conditions. Okay, neutral axis outside the flange and DF greater than 3 by 7x. In the previous problem, right, just observe, we have taken DF less than 3 by 7x. But here in this problem, let us consider DF greater than 3 by 7x. Now as soon as, if you consider this condition, that is DF greater than 3 by 7x, there will be one more term comes into picture, that is YF. Okay, so for the second condition and you are assuming, then we are going to consider one more term, that is YF. So this YF is known as height of equivalent stress block of uniform stress. Okay. So this YF will be nothing but here. This is the YF. Okay. This is the YF. Okay. Now, how to find this YF? Okay. So YF will be calculated as 0.15 XU plus 0.65 DF. Okay. So let us consider the term YF is equal to 0.15 XU plus 0.65 DF. Okay. So therefore YF is equal to 0.15. Keep XU as it is. We have to calculate that XU plus 0.65 and DF. DF is given, that is 100 mm. Okay. Now substitute this. So this automatically the term comes 0.15 XU plus 65. Okay. So this is nothing but YF. Okay. When you are considering this condition, DF greater than 3/7 XU, first calculate YF using this equation, that is 0.15 XU plus 0.65 DF. Now this is the equation. Just write it as equation number 1. Later we are going to use this. Okay. Now again come to this. We are assuming neutral axis outside the flange, that is XU is greater than DF. So for this condition, above this portion, this is the compression zone, and this compression zone is divided into two rectangles. So this is rectangle 1 and these two are rectangle 2. Okay. Now this is a tension and this portion is compression zone. Now equating total C is equal to total T, that is total compressive force in this portion is equal to total tensile force in this steel. Okay. Now as usual, minor changes we are going to observe here. So 0.36 FCK. So for this rectangle 1, what is the stress? 0.36 FCK will be the stress, and the area of this rectangle 1 is BW into X. Okay. 0.36 FCK is the stress, area is BW into X. Plus, so stress in these two rectangles. Okay. Stress is 0.45 FCK. Okay, 0.45 FCK is the stress, and area of this two rectangles. So this is BF. So BF minus BW. This you have to remove. So BF minus BW will be the length, and what is this height? Height will be YF. Okay, height will be YF. So if you consider the previous problem, here we have taken DF, but here this condition, because of this condition, wherever DF is there. Okay, wherever DF is there, you have to put YF, the term YF. Now in the previous problem it was DF, now we are going to put YF. Okay, so this is C1 plus C2, that is C, that is equal to T. So what is T? Total tensile force in this T bar, 0.87 Fy is the stress, and area of steel is AST. So C is equal to T. So from this, only change is observed here. In place of DF, we are going to put YF. So substitute all the values. So 0.36 FCK BW, XU keep as it is, plus 0.45 FCK BF minus BW into YF. What is YF here now? So YF, substitute this equation 1. Okay. So YF is equal to 0.15 XU plus 0.65. Okay. That is YF is equal to 0.15 XU plus 65. That is equal to 0.8745. Okay, into this AST 2946. So from this equation we can get XU value. Okay, so here we can get the neutral axis depth. Now compare. So this XU will be compared with DF. So why we have assumed, what is the condition we have assumed? XU is greater than DF. Now what is XU? XU is 163.9, and what is DF? DF will be 100 mm. That is, this DF is 100 mm. So whether XU is less than df or greater than df. So xu is greater than df. So what we have assumed? xu is greater than df. So this condition is satisfied. Okay. Now let us move to the next step. Another condition we have assumed that df greater than 3 by 7x. We have assumed df greater than 3 by 7x. So 3 by 7 xu just now you have calculated this value. So substitute xu 3 by 7 163.9. So this is 100 and this is 70.2. So automatically df is greater than 3 by 7x. So both the conditions are satisfied. One is okay, that is neutral axis xu is greater than df, and second condition df greater than 3 by 7 xu. Okay. Now after the two conditions are satisfied, now let us check whether this beam is under reinforced or over reinforced section. For that we are going to calculate xu max. So for Fe 415 grade steel, xu max is equal to 0.48 into D. So 0.48 into effective depth is 500 mm. So this comes out 240 mm. Now compare this xu and this xu and this xu max. Whether xu is less than xu max? Yes, xu is less than xu max. So the section is under reinforced section. So this T beam is under reinforced T beam. Okay. Now final step is okay. You have to calculate the moment of resistance, that is factored moment mu. So as it is in the previous problem, what we have used the equation with small change, we are going to use the equation, that is C1 here, this 0.36 FCK BW into XU is C1 into lever R plus C2 into lever R. Okay. So what you have written here, this C into lever R. Okay. C is C1 plus C2. So C1 into lever R plus C2 into lever R. Again observe the change here in this equation. Same what we have used in the previous, but what I told, when this df is greater than 3 by 7 xu, wherever the df is there, you have to put yf. Now in the previous problem it was df. Now in place of df we are going to put yf. Here also it was df by 2, but now it is yf by 2. Okay, same equation we are going to use. So substitute all the values. Now yf again you have to calculate in equation 1. We have written this equation 1. Okay, so that is 0.15 xu. Now we have calculated the xu value. Substitute this xu. Finally, you can calculate this yf. So that yf is equal to 0.15 into xu. See here, this xu is 163.9 mm. So this yf comes out 89.59 mm. So this is the factor 89.59 mm. Now wherever the yf is there, you can substitute this 89.5. Remaining things it is known. Okay. So calculate final ultimate moment of resistance. So mu will be 476.57 into 10 to the power of 6 Newton mm. Okay. It is in terms of Newton mm. If you divide by 10 to the power of 6, this will going to be your kilonewton meter. That is 476.57 kilonewton meter. That will be the ultimate moment of resistance of T beam. Okay. So this is the problem in which we have assumed the condition, no doubt neutral axis outside the flange, but we have considered df greater than 3 by 7 xu. So if you are considering df greater than 3 by 7 xu, then first take this term yf. Okay. Then write this equation 1. Then as usual change this. Okay, change this equation, that is c is equal to t. So wherever df is there, you can put yf. That is the only change. In this also, and in while calculating ultimate moment also, wherever df is there, you can put yf, and yf is calculated using this equation. Okay, so this is also an important problem. So you may get in the examination. That is, when the neutral axis outside the flange, okay, So there will be two conditions, that is df less than 3 by 7xu or df greater than 3 by 7xu. If it is less than 3 by 7xu, whatever the yesterday's class we have solved the problem, so please refer that problem. Now if the df greater than 3 by 7xu, this is the procedure we are going to be followed. Hope you understood this problem. Okay, once again solve these two problems, that is today's problem and what we have solved in the yesterday's problem. Okay, solve these problems. If you have any doubt, so feel free to ask me. Okay, so because in the next class we are going to start with the module number 3. Now till now module 1 and module 2, whatever we have learned, all these are analysis. Okay, analysis of singly reinforced beam, analysis of doubly reinforced beam and analysis of T-beams. Now let us move on to the next module in the next class, that is module number 3, design of beams. Okay, now we are going to start the design, actual design in field, actually in the practical, how we are going to design the beams. That is, it may be singly reinforced beam, it may be doubly reinforced beam or it may be T-beam. How we are going to design the beam. So now here onwards, that is module number 3, module number 4 and module number 5. So module number 3 is design of beams. Okay. Module number 4 is design of slabs and design of staircases, and module number 5 is design of columns and design of footings. So here onwards there will be a design problems. Okay. So thank you very much for attending this session. So once again I request practice these problems. So if you have any doubt, so ask. Okay. So thank you very much for attending this session.